Okay. Let's see. So approximating areas algebraically at this point, which is called the Riemann sum, as opposed to, I suppose, I don't know, the Greek sum or Archimedes sum or whoever came up with that idea for the first time. Yeah, so they knew geometry well, but not they didn't have neither coordinate system, no idea of functions or anything like that. So that it took a while. Actually, if you want to think of Riemann sums, that would be already 19th century. Okay, so then it worked out pretty well. Again, if you remember, this is what happened. This is our approximation with the this one. If it works out, especially if we have 20 intervals. Okay, so with 20 intervals, our -1 interval is subdivided into smaller intervals. This time it's 20. The width then is 0.1, as you can see, and then the heights are found by sampling our function, which is square root of 1 minus x squared. Okay, and then as you can see, we proceed from left to right each time, computing the areas of each of them by simple multiplication. Okay, so like this, yeah, it is just multiplication. Okay, here it is. And then we're adding up all of them together, and once again, do you remember what happened? The sum is very close to pi over 2. Well, somewhat close. Okay, so if you have 100 intervals, then the accuracy increases significantly. So now we're trying to develop a theory that will work every time, at least a theory that will work in theory. So that's the repetition of what this is, Riemann sums. And then we started the next example, which to take it all the way through and to see where the challenge is. And the challenge is, right, we reached it right at the very end, is the challenge is for the computation with infinite accuracy is that it has to be, the whole construction that we have done with the circle has to be dependent on n. Any n. It should be carried out pretty much like simultaneously for all possible n's. And so then the answer, that is a specific number. When you just want an approximation, you don't care how accurate it is, just a number. But if you want absolute accuracy, then you got to take the limit, so you have to have a sequence. Okay, so that's what we're trying to produce, a sequence of Riemann sums. So even though each Riemann sum is made of those n intervals and n elements added together, but then we take the limit of that. Okay, so that certainly is very simple. So this part isn't too bad. This one. So that is this is the definition. Okay, so heights time height width, and then the function is specific right at the top. So they plug in, and as well as the sample points. So these are the sample points. Left and in each interval is chosen as the sample points. So these are in pink. These are the sample points. Okay, and then we substitute it, and we end up with a complicated sum, which we were able to simplify somewhat, and this is where we are right now. Okay, so this is the part that might be possible to simplify. I mean, it is possible to simplify, even though it's not especially easy to see how, and but otherwise it's pure algebra, just to know, and so that's the goal. Simplify. Why do we want to simplify to begin with? Because right now we're supposed to take the limit of this. So where does this go as n goes to infinity? The answer is very complicated. We never faced anything like this because that in the middle is the problem. Okay, so we've done many limits, but we always had a specific formula, right? In this particular case, there is no specific formula just yet because look at that sum that, well, if you look at the whole thing, the thing is that that dot 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 in the middle is something that ever happens every time with the Riemann sum, because n, what is n? We don't know what it is, not specific. And then what happens if you look at, say, this expression over here, it is n, as we progress to better and better approximations, we have more and more terms in the sum, but each of these terms getting smaller and smaller, right? Think about those about these bars. So if I put here, I think I did it last time, but if I put 100 here, they're gonna be there will be still 20 of them because that's how much data I've got, but they're gonna be thinner and thinner. Okay, so but there are more and more of them. So that's the problem which we cannot handle unless we do this algebraic trick, and fortunately that is possible. There is a formula for that, for this, what I have in the circle. There is a formula for it. It is n minus 1 cubed over 3 plus n minus 1 squared over 2 plus n minus 1 over 6. So somebody did some work, mathematical work, to find that formula. Okay, so sometimes it's easy, but frequently that's example of which not. So instead of having n terms, now we have 3 terms. Okay, so it looks kind of complicated, but really, if we think about it, it's not that complicated. So then we can, because why it's not complicated, because we really don't care about the exact what it is equal to, but rather its limit. What is its limit? Let's examine what it is. Okay, so let me write it out one more time. Here's what it's going to be: 1 minus. So I'm doing common denominators here. 1 n minus 1 cubed over 3 n cubed minus n minus 1 squared over n cubed again, plus n minus 1 over 6 n cubed, and here I have 2. Okay, taking the limit. Okay, so as n goes to infinity, 1 remains 1. Where do these go? So n goes to infinity. What are we looking at here?
Wouldn't they go to 0?
What?
Would they go to 0?
Some of them, not all of them. So look at the very last one. It goes to 0 because right. It is not just faster. It is more powerful. It has higher power. The degree is 1 in the numerator. Degree is 1. Degree is 3 in the denominator. And so the denominator overpowers the numerator and it brings it to 0. Same story is with this one. Power is 2, right? Compared to 3, it is bigger. And so we are left only with this, where the powers are equal. So where does it go? Well, when the powers are equal or not, the answer was the same. Look at the leading term. What's the leading term of the, and the rest are not important, you can just throw them out. So what's the leading term of the numerator?
1.
Leading coefficient, yeah. So what's the answer then?
So it goes towards 0?
No, the leading term is the highest power. The highest power in the denominator is 3n cubed. What's the highest power in the numerator? But it's not expanded. Imagine that you expand it. What's the highest power? I mean, you multiply n minus 1 by 3 times by itself. The highest power will be what? n cubed. No, there's nothing tricky here. There's just I mean, if oh, well, there's a formula certainly how to expand a binomial into the third power, to second power, third power, whatever. But imagine that if you multiply three terms, three factors, identical factors, then the only way to get the highest power, which is 3, is to multiply the first term, first term, first term. So n minus 1, n minus 1, n minus 1. So if you start multiplying, you will end up with 8 terms, right? But only one of them will, when you multiply these 3 by each other. So that produces n cubed as the highest power, the only term with n cubed. So so the limit is 1/3. So the whole thing is 2/3. So that is literally our conclusion is the area of the graph is exactly 2/3. So all the approximations are good, but they're just that, approximations. So if we are actually going with the actual accuracy, well, there you go. That algebraic formula helped us a lot to resolve this issue. So some of the formulas are more complicated, some simpler than that, but this one is the one that is circled in yellow. That transition is the hardest part because it takes algebra, and it is not very well. It's advanced, and you never know if there is a formula. It happens all the time. You have some expression you want to simplify. Does it really simplify in this manner or not, or there is something very awkward about it? So the conclusion is that even though we have been successful, you can do the same with the circle or a lot of other curves. That is really not a method. You don't want to apply it all the time. In order, you want to compute maybe many areas, and then the exact values, and you don't want to get into this algebra over here as we did. We skipped it, but somebody did all the work for us. So that's why we are moving in the direction of ultimately understanding areas in terms of other concepts of calculus, and the answer is we're going to be dealing with antiderivatives instead of limits. So limits ultimately will be, how should I say, transcended, just like remember they were transcended when we did the derivative. The derivative was defined and always to be remembered as a limit. Right, there's a limit of the difference quotient. However, we haven't done computing limits, computing derivative as the limit since the last test, and the same will eventually happen with the integrals. So they are also computed as limits initially. They're defined as limits and always to be remembered as limits. But ultimately, if the issue is computation, then there are other better ways. Okay. So let's try to have a general setup for this with all this background and build-up is available now. So let's start over and try to have with an abstract function. So we have we given a function y equal f of x over defined over interval ab. And what we want to do is to estimate the area, approximate the area, and then what we want actually, probably a better way to describe it is to define, we're still at that stage, define the area under the graph. And define, what does it mean, define? It means that we want to sort out mathematically what its meaning is. We already have the idea, but I just want to start over and set it up very, very carefully because we know we don't need to define the area of a rectangle. It's width times height. Okay, but beyond that, you can get triangles in the same fashion. The area of a triangle is simply half of the area of the rectangle. Okay, so that elementary geometry gives you that. But beyond that, what is the meaning of a circle, or the area of a circle is if you have a curved shape, then you got to start from scratch, and the only way to actually sort it out is, frankly, is the limit. So we got to set up a limit that at its end, if it exists, will produce a number, which that number will be said to be the area. Okay, so that's what we have here. We have the interval from A to B. Okay, so we cut the piece of the graph from this, and this we are after this area. So once again, the top is it is simpler a bit than what the ancient Greeks did, because only the top is curved and the rest are straight. Okay, and but that's not the why we're doing, because the point is that we're gonna be able, we have been able, and we will be able to compute those limits, one directly or indirectly. So okay, so then the next step is what's called a partition. So we partition, it is either verb or noun, doesn't matter. So we partition AB into n intervals. N being our major parameter. Remember, major parameter, how many intervals we've got, and that number will be taken to infinity. Okay, so into n intervals, which generally does not have to be equal, but it could be. So that's the length is delta x equal b minus a over n. Okay. The word partition is means that you split the set into non-overlapping subsets, and in this particular case they do overlap, but not more than we're ready to accept. So meaning that they only have one point in common. Every two adjacent segments have one point in common. So so the points are a is equal to x naught, less than or equal to x1, less than or equal to x2, xn at the end, which is b. Okay, so once again, this is a and b, and starts with x naught to xn. As you can see, n plus 1 points, well, what we usually call them, we call them the endpoints, because they are the endpoints of the intervals. And the total is the n intervals, right? N intervals, n plus 1 endpoints. Okay, so you look at the points, but at the same time you have the the intervals. Okay, so then delta x, it's the length of the interval, but it's also delta x equal b minus a over n. It is also the width of those bars, of each bar. They all have the same width. So that's number one. Number two, the heights. So we just need now to determine the heights of those bars that we're going to be approximating. So that at this point we do neither what we did. We have pick the left end of the interval, or we could pick the left end. So this is the interval. You could pick this point, left end, or you could pick the right end. So left end, right end, this point, okay, middle point as well. So point in the middle, but generally we don't impose a restriction, and they are simply arbitrarily chosen. So that's how we do it. We call them sample points. So choose a sample point in each interval. Okay, so we call them, say, S sub k. Say S1, Sn. Okay, so n intervals and sample points, and the values at these points, values of f, will be the heights. Okay, so that's all there is. So let me take one. Suppose this is my interval. Let's say xk plus 1. Okay, then I have somewhere in the middle an unspecified s sub k. Okay, and then what happens next? So that's the step number 1. Step number 2, I go and I'm sampling the function. So from the point sk, I'm going vertically until across the graph of the original function. Okay, so this is y equal f of x. I find where they cross, and then this is the height. F of sk is the height of the rectangle. In fact, so this is the actual computation. Will be computed, right? So sk is given, so I'll find the value. But you can illustrate it with a little picture. Actually show the rectangle. So the width is at the base of it is shown at the bottom, and then this is the height. So how do I do it? This is I just sort of follow this length, follow the top that we have found, follow it to the left and to the right. So I go from xk, the left end of the interval, up, and all the way up, meaning not non-stop. Okay, so the left end and the right end. That's not good. Okay, like this. Okay, so that is my board. It's kind of thin, but you can certainly see where it is. So this is my board. So its area then. The area then is equal to f of sk times delta x. Okay, so delta x, once again, the width of the base, delta x, and this is the height. Well, here's a question for you. What if the function is negative? What if the value of the function here is negative? No, it is natural inclination to follow that, and it took a few hundred years to sort that out. But actually, we keep it negative. We just end up with negative areas. It is maybe take time to get used to, but negative areas makes perfect sense. You think about once again, take the metaphor of motion. Our function is in fact our velocity. Velocity could be negative if we're moving in the opposite direction. So we've chosen the positive direction. If we're moving in the opposite direction, then our velocity is negative. And then our displacement, which is what this area is also negative. And then it could be positive, negative, and we'll just and they cancel each other possibly. So it is possible. Totally, the plan of ours works out even if a function might look like this. Okay, and then this goes as positive, this goes as negative. Okay, and that's okay. So the area could be 0. The function that goes up and then down below the x-axis could add up to 0. It's possible. It's possible. So if we are interested, so we kind of expand the idea of the area from just being a number which is either 0 or higher. Now it could be also negative. So it's a kind of an expansion a little bit, but it pays benefits. If you really need then if you need a physical area in the original geometric sense, then you do add absolute value to f, and then instead of doing the same procedure will be simply f replaced with the absolute value of f, right? So that certainly is the way to go if your interest is actual geometry. If it is either motion or anything more complicated than that, and it usually is, then we do not, we keep it as is. Okay, so then the total area, that's the next step. the total area is the sum so is equal to f of S1 delta x plus f of S2 delta x plus f of sk delta x. Okay, called the Riemann sum of this sampled partition. So sample partition means not only those intervals, but also the chosen sample point within each of them. So that's what sample partition is. Okay, so Riemann sum, it still only approximates, but ultimately the conclusion is that the Riemann integral is the limit of the Riemann sums as n goes to infinity. Okay, in other words, this is the notation. We use the symbol, either f of x or f dx, doesn't matter. So the limit with n going to infinity, and I'll just repeat the sum here, f of s1 delta x, f of sn delta x. Okay, so I don't want to skip necessarily from Riemann sum to Riemann integral. It is ultimately what we want to do, but Riemann sums are so much simpler than the Riemann integrals that you can figure out a lot of things about Riemann sums just sticking with about Riemann integrals if you just stick with the Riemann sums, because Riemann sums are just sums of numbers at the end. If you study them before you deal with the limit, this limit is certainly, as we just saw, is not that easy, then you can get pretty far. So that's the Riemann integral. The notation, as you can see on left, is related to the notation of the this one. It is related to the notation of the derivative. So that dx should be recognized once again as one whole thing, so it's not multiplication. You can see where this comes from, the notation. So first of all, the limits. So the x runs between. You can let me maybe expand a little bit on this integral on this notation. So it's x equal a runs x runs from a to x equal b. Okay, so that would be not an unfair way to put it. Here I have f of x, and here I have dx, which is, remember what has happened is just as we did with the derivative, delta x is turned into dx when delta x goes to 0. You know, when n goes to infinity, delta x goes to 0, right? So because you divide the b minus a over n, so that's what delta x is. So delta x goes to 0, just like with the definition of the derivative. Okay, so and then the same substitution, kind of a sleight of hand, we replace the dx with delta x is replaced with dx. Okay, so that's the same trick as in with the derivatives. Okay, the function certainly is here clear. The symbol is always thought of as the stretched word s, a letter s, which stands for the word sum, okay, or summation. Okay, so everything comes from summation. In fact, that's what we're going to do next, is a little bit of notation that is necessary for the way we proceed. But it is fairly straightforward. That's where it came from. Somebody took the word letter S, stands for sum, and stretched it vertically, and we have this weird symbol. Okay, so that is the whole thing, almost. Certainly there are issues that have to be pointed out right now. As always with the limits, the issue is what?
It can be undefined.
Not they could be undefined. They could simply not exist. Right. So we have to say when the limit exists, f is called integrable. Okay, so more terminology. In addition to, remember, we already had two big classes of functions. What are they? The two big classes of functions? No. This is a too small. Linear is just too small a class. No, the two others related to. One was related to limits to begin with, and the other one related to derivatives.
There has to be a limit.
Yeah. Okay. So if the limit exists, then what do we call that function? That if the limit exists and equal to the value of the function is called continuous. So remember now, so continuous. What? No, continuous, and what about when the derivative exists? What's the word? What do we call functions with derivatives? Well, those are the functions with derivatives. They're the ones that we can differentiate. So, what's the word? Differentiable. Right, differentiable. Remember the relation between them? Continuous and differentiable. Every differential is continuous. Every continuous and differential, which way does it go?
Every differentiable is continuous.
That's right. So this is how I would put it, like this. So these are differential, and then the continuous. There are more continuous functions like this. So continuous functions include differential. Now the good news is that integrable is even bigger. So like this. So in other words, what I'm referring to is this theorem. Every continuous function is integrable. Informally speaking, it means that if you draw a curve continuously like this, then the area under the graph of this curve makes sense. You can think of things when it does not make sense. So let me give you a quick example. And that is, for example, how about 1 over x? So you can see what the problem with this is. It is not continuous at 0, and can you see what's happening to the area? It keeps expanding. You probably, if we try to carry out Riemann sums here, we might end up with infinity. So it's possible to end up with infinity. Not always. Sometimes you have infinite area. We'll have to wait on your calculus too. But sometimes the area looks infinite, but actually, I mean, the region looks infinite, such as this, but the area is not. Okay, so it's also possible. But it is a possibility that why this function is not covered by our theorem, because it's not continuous, and because it could be a function looking like that might end up with infinite areas, which is not really part of what we have. When we say limit exists, we say that it means that that the limit is a number. Okay, so we still think about areas as numbers, even though now we can think of them as negative numbers as well. Okay, so every continuous function is integrable, but just like here, you can see there is room left. Not every differentiable function is continuous, but not every continuous function is differentiable. The example is what? No, the function that is continuous but not differentiable. The absolute value, right? Okay. That's all. As you can see, continuous curve, and but there is no derivative at 0. There is no tangent line. You can also think, realize that this function is integrable, right? So it's really not hard to understand that the area, this area, makes perfect sense. It's made of triangles, right? So the fact that the function is not differentiable does not really stop us from integrating it and from understanding it's the area under the graph. So I mean, it's made of straight lines, so what's the problem? But there are functions also. We are also in a similar situation here. So every integrable function is every continuous function is integrable, but not every integrable function is continuous. Okay, it's really very easy to think of an example like this. Okay, maybe like this. Okay, so think about it. A function is certainly discontinuous, right? But at the same time, does the area under such a graph make sense? Sure, why not? Like this. Like this. This is the area. So the instant jump up, which we have run away from for a while because the function is discontinuous, so there is something wrong with what's going on. The curve has a gap, so it's like if that cannot describe motion, because then it means teleportation from one point to the next, and that's you don't want to build a physics on that, well, at least not elementary physics on that foundation. But as far as integration, as far as area is concerned, it's okay. So once again, it is a jump, but the area still makes sense. Okay, you look, it's made of two rectangles, no problem. In fact, it would be very easy to compute the Riemann sums for it. Now, and also now let's think about velocity. So when the function represents the velocity, can it change instantly? It appears that it can. So it is maybe a physics that not really, well, it's certainly easy to accept instant change of velocity than instant change of location. Right, because instant change of location is a teleportation, right? Instant change of velocity, well, even though we probably can think of, circumstances when it does happen, but at least you can imagine. So they're just instantly accelerated, but it did not jump from to the next place. So once again, this is okay, and we have this hierarchy of functions: differentiable, more continuous, more integrable. Okay. But there are still functions that are not integrable, so it's not ideal situation. Okay. Okay, so there is one more attempt to generalize the Riemann sums. We already have negative areas. We certainly can have zero areas. And when the function is zero, but it's also will be a zero. We are talking about areas right now for the most part, not really motion or anything like that. So if f is equal to 0, right, then naturally integral from a to b fx dx is 0, right? So the area under the graph, the area under the graph, by the way, it is a little bit of a misnomer because we're talking about once we understand that the function can go below the x-axis, it's not below anymore. It's probably better described as an area between the graph and the x-axis, right? So that makes more sense. So we're talking about this is positive, and then this is negative. So negative, and this one is positive. So when we're computing the area, we add those green parts and subtract the purple ones. Okay, so once again, the point I was making is that we're talking about the area between the graph and the x-axis. Okay, but either way, if your function coincides with the x-axis, then there is no area there, so the answer is 0. But there is another situation when you can conclude that the area is 0. What if the integral is 0? So a is equal to b. Integral from a to a fx dx also equal to 0. Right, so then because there's no width, you can even go with Riemann sums, but the width of each of the elements of Riemann sum will have 0, so you end up with 0 inevitably. There is, however, even you can even take it further, and that is, so in this particular case, we're talking about integrals of fx dx with a equal to b. Originally, we started with a less than b. Now we're talking about a equal to b. It's also possible to talk about a larger than b. Okay, so this was, it is, once again, you have to stretch your imagination a little bit in order to accept that idea of what happens, what is the meaning of the area when from A to B. The area is still from A to B. Okay, so this is, if you see something like this, this is from A to B. But this time, what if, I mean, these are just two numbers, so why not just to say that why one of them larger than the other, which one? So A here, B here, okay? So try to think of the meaning of, can you think of the meaning of such the area? The area from A to B, but B is less than A.
Would it be the same?
No, it actually matters in which direction we're going. This arrow is actually very important, becomes very important, because there's a positive direction of what? We just talked about the positive direction of y, right? When we ended up with a negative area when what? When our velocity was negative. Okay, so it's possible now. So that's why the direction of y matters. The direction of x also matters. It's like the direction of time. Okay, so we know which way time goes, and when we are talking about time from A to B, when A is less than B, it means that the time has reversed, right? So we're talking about our displacement, except moving backwards in time. So if I moved, so suppose I for between 1 o'clock and 2 o'clock I drove 100 miles. Okay, now, and that's my displacement. If I now try to think backwards and I rewind the film or use a time machine, then what's the displacement? Negative 100 miles. So you move backwards, right? So if you start moving back in time, then your displacement changes to the negative. So that's why we expand that idea to just say from B to A, fx dx is equal to negative from A to B, fx dx. Okay, so all covering all bases. It is possible, quite possible, that the direction is not predetermined ahead of time.
Would there ever be a reason to find the area as pertaining to the y-axis and not the x-axis? Let's say you have a straight vertical line. Finding the area between that, would that mean anything in terms of...
I'm not sure. I mean, so if it is not a function, then it's hard to think of it as motion. So we have been thinking about if x is time, then y is the location. If it is that interpretation, then a function that whatever we have which is not a function, then we cannot be simultaneously in several places. But generally speaking, if we are talking about geometry, then it doesn't matter really. X and Y are just our they are our helpers. We want to compute anything we want to compute. So, for example, maybe this is my function that just happens to be, the graph is located this way, and I want to compute this. Right, so what is the difference? There is not a big difference. It's going to be, this will be x equals, say, g of y, and I will be doing integration of g of y dy, say from c to d. Okay, so it's all possible. right? So it just depending on what kind of problem you're dealing with, and if the problem is truly geometrical, then you probably start with something that is maybe unspecified in terms of functions, and then you choose the functions. And if you find it more convenient to speak of functions as functions of y rather than of x, then it's up to you. So just take the circle. We prefer to cut the circle when we compute it horizontally in half, and then take upper half, which is the graph of a function of x. But we could have done this, right? And the effect would have been exactly the same. So there's really nothing special about the relation x and y. These are tools, pretty much, for all we do. So okay, so and now we are moving towards the algebra of this. Both Riemann sums and Riemann integrals are just side by side, so that from something simpler, Riemann sums, whenever we can, through limits, we move to something more complex, Riemann integrals. So Riemann sums is made of those bars. Riemann integrals have the areas of a curve with regions with curved top. Okay, but there are certain properties that algebraic properties. What happens to the integrals when we do algebra with functions? So algebra of functions is, remember, we used it a lot. So f plus g, f minus g, f times g, f divided by g, and then decomposition too. Okay, so that's the algebra function that I have in mind. And remember that we had for all 5, we had limit laws, right? Limit laws, so we're gonna need those. And we also had for all of them, we had derivative laws. Remember the sum rule of derivatives, and so on. So say f plus g prime is equal to f prime plus g prime, and so on. Okay, so now we're in a similar place, not quite as far, but in a similar place with integrals. The situations for now is simpler because with differentiation we already know that the output of differentiation is a new function. So f was my function, and then that which is the input of differentiation. The output of differentiation is the derivative, which is another function. Okay, so these are all functions. And that's the complexity that we have to face, had to face, and now we are facing something that is kind of not as complicated, because after all, the integral is a number. And remember that at least for the time being, there will be some variety to that, but for the time being, the integral is definitely nothing but a number, and the meaning is the area, but otherwise, the integral is a number. So then we ask ourselves, what if we do these operations with functions, what does it do to the integral? And the answer is very simple. For the first two, it is very simple, and for the rest of them is not only very simple, it is quite complex, to say the least. So let's just look at these two. Well, there was one more that I missed, is the constant multiple rule. This one is a pretty good. That was also okay. So these 3 for the time being we can do. Okay, so starting with the sum of two functions. Think about this. If so, we have one function and we have another function. So see, this is f and this is g. Okay, maybe it is not quite easy to understand what their sum looks like. But if you think in terms of Riemann sums, it is possible to understand. So suppose I have a few Riemann sums, some bars for the Riemann sum of f over the same interval. Okay. So can you imagine what the sum of them looks like? So I want to plot here f plus g. I want to plot the Riemann sum for f plus g. What do I do?
You add the bars.
I add the bars. So I plot the same bars. So I plot the same bars from G, and then I put the F bars on top of it. Okay, let me try to do this like this, and this one is longer. It's about the same. Okay, so that's the, it doesn't matter really, it doesn't matter what the actual graph of F plus G looks like. We care only about the Riemann sums. So if this is Riemann sum of F, and this is the Riemann sum of G, then this one, the Riemann sum of F plus G. And every time we did it one by one, we put the bar, well, two bars on top of each other. So then what's the relation between these three numbers, 1, 2, and 3? That's right. Yeah. So So Riemann sum of F plus Riemann sum of G is equal to Riemann sum of F plus G. Okay. And then what we do, we take the limit. Limit as n goes to infinity, and we apply the sum rule. Sum rule for limits. Then this one goes to what? Riemann sum of F goes to the integral for F, right? From A to B, according to the definition. This goes to integral for G, and this goes to integral for F plus G. Okay, to begin with, so that's the definition. According to the definition, we have these three Riemann sums go towards the Riemann integrals if the functions are integrable, and then the sum rule for limits provides us with this. The sum of the limits is equal to the limit of the sum. Okay, so and the result is then is this, and it is called the sum rule for Riemann integrals. You can look at this one as the sum rule for Riemann sums, but then under the limits, with the help of the sum rule for limits, we end up with a sum rule for Riemann integrals. So that works almost identically to how we apply the sum rule for differentiation. It is a shortcut. So if we know the integral of one function and the other one, we don't have to start from scratch. We just add them together and we have it. The conclusion is less than obvious if you think about it. In terms of those bars, it's kind of obvious, right? But if you think about actually curved regions, then adding one on top of the other is simply impossible, right? So if you have two semicircles, how do you add them together? You know, this is one and this is the other. It's really not possible to. You got to kind of push it one into the other with the, I don't know how. It's like think about some made of clay or something like that. But fortunately, we have all the tools to demonstrate that it is exactly what happens. So to add two areas, we add the functions that define them. So that's another way to look at it. Adding areas means adding the function that represent upper borders. Similarly is the constant multiple rule. So we have a function f y equal f of x, right? And then I have my bars of my Riemann sum, and what I'm doing here is I'm trying to then think about what if, say, I multiply by 2. If I multiply f by 2, then what happens is each of these bars will double, right? So it's will be similar, somewhat. Like this. Okay, so this is Riemann sum of twice f of x. So this is Riemann sum of f, and this is Riemann sum of twice 2f of x. So once you see the relation between the two Riemann sums, then what you do is just look at where does this one goes towards integral of f, right? And this one goes to, as n goes to infinity, by definition, this goes to twice f of x. But at the same time, we know that this is twice as big. Right, so I took those bars and I doubled them and then put them on top of it. Doesn't matter where I put them, the area is twice as big. So which means that if I multiply this by 2, if I multiply this by 2, then I'm going to have this. Right? So in other words, we discover that we discover this about Riemann sums rather than about Riemann integrals. But under the limit and the constant multiple rule for limits, we make that conclusion. So the equation becomes what constant multiple rule for Riemann integral is so integral c f dx. We can pull c out just as we have with derivatives. So the assumption is the same, f is integrable. Okay, so in here also we have to require f and g are integrable. Okay, so these are the two nice shortcuts that we can employ whenever necessary. But then once again, now the trouble is, of course, the things are more complicated than differentiation, and even though we look at one number at a time rather than whole functions, but it's very hard to imagine what the multiplying two functions does to areas, because for one, all of this kind of construction disappears simply because there aren't any areas anymore. They become so if remember that our interpretation of this was that the heights of these bars were values of f. So in other words, f was like a measured in feet. But when you multiply f by g, both of them measured in feet, then the product is already becomes area. Okay, so the analogy with areas that we utilized just now disappears. So that's why, in a sense, there are no product rule nor quotient rule. There's a in calculus 2 you'll see some analog of the product rule, and later on in this course we're going to see the composition, something like a rule for integration of composition. At this point, these are the only three rules that we have, which means that it will be very hard to do integration of functions beyond the simplest one. Right now, what do we know? We really don't need to know a lot about the integrals. The only one I can offer you, in addition to what we did early today, and the circle, is the constant function. So that it is really elementary. So what is the integral of c dx from a to b? So the function is y equals c. Okay, this is a, this is b. You can run out the Riemann sums if you like, or you can just give me the answer. B minus a times c, that's right. Notice that the formula, this is the answer, the rule for constant functions. Notice that it totally includes the possibility of a negative c, right? So area negative. It also works out just fine for the case when B is less than A. It also works out just fine, right? So still it becomes negative right away. Okay, so one thing is worthwhile to notice before we do more of Riemann integrals is the relation between the Riemann sum and difference quotient. So the two things that we defined before we did the before we did limits. So let me just let's point out a few things. So difference quotient. Right, so so a function, you do a similar thing in a way. You sample it, sample the function, right? And you can sample the function the same exact way as we did with the with integrals, except you sample it at the endpoints. Okay, so these are the endpoints, and so if I have my function, then I look only at these values, and then what do? I subtract. So once again, I'm doing difference quotient, something that we started with early on, and then we use it to build derivatives. Okay, so then then I have, what do I have here? Once again, x1, x2, x3. So the difference quotient will be say f of xk plus 1 minus f of fk over xk plus 1 minus xk. Okay, so this is the rise. I'm sorry, yeah, this is the rise and this is the run, right? So what I'm talking about is, say, the very first, this is the run, and where is the rise? This is the rise right here. Okay, the vertical part. Okay, so that's the difference quotient, and if you want to, that's the starting point, and all the simulation with Excel that we have done do exactly that. So function is given, maybe coming from a formula from elsewhere, and then you compute the difference quotient. If the intervals are small enough, then the resemblance is very. It resembles integration, differentiation very nicely. What is this I had? Not this one. Well, maybe like this. Well, it's not, once again, not quite the right one. I don't see it. Well, so we did it. I just can't seem to find it. The function is if you do it by hand, or with Excel, that is, or you do differentiation of a function, actual differentiation, things look just about perfect. So if you start with a function looking like that, its derivative will look like this. Okay, so you just do it, nothing but this computation. We did it a few times. That's how you produce from physics. You produce a parabola, motion in space. So this is just y equal f of x, and this is I plot its difference quotient over here as a function. Okay, one by one. So that when these intervals are so small that we don't see the difference, then this is will be my graph. So everything is very close to what you would expect to have when you do actual differentiation. Okay, so that's the difference quotient as until we, from this, the next step, which is I actually intentionally want to ignore for the time being, is the step towards under the limit, and it takes us towards the derivative. Okay, so but suppose we don't take that step and we just keep the the difference quotient for our purposes, and we do modeling. Okay, it's just as that's the only way you can do it really, any kind of model on a simulation if you do your projects. So now we are reversing the direction. So we ultimately will see that this is a reversal of direction. We are talking about Riemann sums. Okay, and there we'll also have seen them. We have seen Riemann sums if you before, even when we talked about the areas. Remember the whenever that problem of broken odometer situation. So this is a broken speedometer. If you have a broken speedometer, you record, see, you sample your speed. So you think of this as speed, you sample it, and then, I'm sorry, hold on, which way? No, I think I got it the exact wrong way. No, this is right. So broken speedometer, how do you know your speed? You look at the odometer. So this is not the speed, this is your location. Okay, so the function is your location. If you compute its difference quotient, then look at it. It is displacement in the numerator and change in time in the denominator. And what do you get? You roughly get your average velocity. Okay, sounds familiar? Okay, and now, so that's the broken speedometer situation. Now, the Riemann sums corresponds to the opposite situation, and that is the broken odometer situation. So you do know your speed, you have your speedometer, but you want to figure out where you are. Okay, so what do? So look at the speed. So this time my function, let's say it's g of x, and then compute Riemann sums on and on and on and on. So remember how it works out? So I look at my speed at equal periods of time, okay? And then what do I do with them? So I don't know the exact speed, but I can sample it. So I sample it, right? So this is the speed. My function g is the speed. Okay, so these are the readings of my speed. So how do I find my location at every moment of time, roughly, just as an approximation?
Take the average of all of them.
Okay, the average multiplied by the period of time, the whole period of time, which is actually totally fine. So this is say A and this is B. I just wanted to show that what you said is a Riemann sum, even if you didn't realize it, because what you're saying is take f of x1, f n, divide by n, the average, and then multiply by a b minus a, right? That's what you said, but if you look at it, what is the meaning of this? No, what I circled. There is a notation for it. B minus a over n.
That's the length.
That's right. It's delta x. In delta x, it is the period of time during which you are not looking, and then you look, and then you pass a half hour and look again. Okay, so then the summation turns into indeed f of x1 times delta x plus f of xn delta x. Okay, so our Riemann sum is in fact simply evaluating, solving an opposite problem of the original. So that's the opposite view, and look at the derivatives and integrals comes from right here, from the opposite direction of difference quotient, getting the speed from location. Speed from location, that's number one. Number two is the opposite. location from speed. So you see how they work in the opposite direction, and that's how we are going to proceed when we get to the derivatives again. So this is all kind of numerical, and what happens before you get to the limits. But then, as you take the limits, the opposite, these two remain opposite to each other. Differentiation and integration, they're still opposite. Okay, so we'll continue this next time. There's certainly a lot of stuff to talk about here.